Today, his topic is engineered water repellents, insights from field and laboratory testing. Professor Daniels, the floor is yours.
Thank you very much. And I trust you can hear me. And I believe,
yes.
Do I have 20 minutes?
Yes.
Okay. Yep. And thank you in advance for keeping me on time. I am so grateful to be with everyone. The International Society of Environmental Geotechnology has been part of my entire professional career. My career has really been shaped by this organization and the leadership, and Bin Shi and H.Y. Fang and Hillary Yin Yang. And so I'm very much indebted to this society and grateful to be part of this. So you see my topic, and I just had a recent change of roles. I'm currently interim vice chancellor of research, which expands my opportunity to serve this university, and I certainly would look forward to welcoming anyone to UNC Charlotte. Some of you have been here, but our institution has grown quite a bit. We're a much larger institution, and we have partnerships all around the world, but especially in China. But throughout the world, we have lots of different formal arrangements, and so we're definitely internationally minded, and we welcome you here to Charlotte. This is from our most recent MOU that we signed with a university in Germany. But that's not why we're here, right? This is more of a technical presentation, and for at least the past 15 years of my career, I've been focused on engineered water repellency. And at the end, I'll share some of my references. But to me, I believe that engineered water repellency is analogous or similar to geosynthetics. And if you think about the history of geosynthetics, like geomembranes or geogrids, these kinds of materials 30 or 40 years ago were in their infancy. They were just beginning, and now they're part of standard geotechnical practice. Likewise, I believe that engineered water repellency is in its infancy now, and I believe in 5, 10, 15 years, this will become a more common method for soil improvement. I believe there's lots of applications because we are able to radically change soil properties. And so the intent of this presentation is really to just provide an overview with some sample examples of insights that my lab has generated at the laboratory scale, with modeling, and then with some field testing, principally focused on one application. But the hope is that you'll appreciate the broader suite of applications that are possible with engineered water repellency. And here you see a picture of what that looks like. By treating the surfaces and rendering them hydrophobic, water simply doesn't enter. And as all of us as geotechnical and geoenvironmental engineers appreciate, water is the source of all sorts of challenges, right? Shrink, swell, leaching, erosion, frost action, loss of strength, all of these things. So if we can control water, we can control many properties. And this figure is meant to show possible applications. By making soil water repellent, we can have benefits with slopes, for excavations, for embankments, and landfills, and so on. So lots of applications. And a lot of this comes to controlling the surface energy and the surface properties. And so this is a figure to remind ourselves what we're typically doing. Soils tend to be, as we see here on the left, water repellent, or hydrophilic, water loving, where the contact angle, the angle that is made with the substrate, is less than 90 degrees. But if we make it water repellent, if we treat it with sustainable and environmentally friendly chemicals, we can make it hydrophobic. We can make that contact angle greater than 90 degrees on the right here. So the goal is to engineer this to make a higher contact angle. And so what that looks like in practice, as you see here, on the left, we see a beaker filled with untreated soil. in untreated soil, virtually all soil, water will infiltrate immediately. If it's treated, that same soil will sustain a positive pressure. And so this is the value of engineered water repellency. In terms of what that means practically, we can characterize this in terms of water entry pressure, contact angle. Contact angle just tells you about the surface properties, but with regard to geotechnical practice, much depends on the arrangement of the particles and how close particles are together and the pore space. And so for natural soils, we have a water entry head that is less than atmospheric, right? So if you think about a soil water characteristic curve, the water entry pressure is negative. We have a suction value. And so the value of the water pressure is negative. But when you render it hydrophobic, it can sustain a positive pressure, as you're seeing in this beaker. And so what this graph also conveys is at very small particle or pore sizes, we have a much larger water entry pressure. Or conversely, if it's untreated, if it's just natural soil, you have a very negative water entry head. Exploiting these relationships, we can engineer water repellency. And so our lab spends a lot of time studying this process and measuring contact angle and seeing how best to test it and how to do this with different chemicals and how ultimately to engineer that. And one of the things that we've learned is that you ought to have a certain threshold diameter of droplets, and that will give you a more predictable value of contact angle. Because if you're going to specify a given chemical, and if you're going to desire a certain level of water repellency, then you want to make sure that your measurement is going to be accurate. So our data suggests that typically it's better to measure the contact angle with an approach of advancing the contact angle, which means growing this water droplet with time. And generally, that the dimension of this ought to exceed 40 nanometers is often what we have specified. Here you're seeing a larger diameter of 1 centimeter. But the point of this is the way in which you measure the contact angle matters. And I'm happy to provide more details on that. You see you get variability if you don't wait long enough. The other thing that's interesting, and again, part of my objective in this short presentation is to provide some insights. In geotechnical engineering, we often think about pore size and void ratio and the degree of compaction, for example, as affecting things like hydraulic conductivity and effective stress and all of that. In the case of contact angle, your value is not really sensitive to pore diameter or the spacing between particles. And to illustrate that, I've got several glass slides here where you can see our hydrophobic surface. You see this glass bead. And even if we really reduce the particles, in fact, you see this droplet is on part of the glass slide where there's not many particles, and yet it's still hydrophobic. And this slide is perhaps a little bit more clear on that part. So we have very few particles on this glass slide, and yet it's still hydrophobic. And that's not because of the glass, that's because there are enough particles that repel the water. And there's literature to support this in material science, which shows that asperities really have little effect on contact angle measurements. And so this work from material science is applicable even to geotechnical engineering. Now, in geotechnical practice, although contact angle is insensitive to pore size, breakthrough pressure is very much a function of pore diameter. And that's a different topic we won't get into too much more here. But those two parameters are important: contact angle and breakthrough pressure. So I wanted to give a quick example of this and highlight a project. And so my broader interest is in engineered water repellency for lots of applications, be it expansive soils, be it overall strength, be it slope stability. There's lots of applications. But I wanted to highlight one example of an existing project. I have a project funded by the U.S. National Science Foundation. It's a collaborative project. I have partners at Michigan State University. I have the link here that I'd be happy to share with people. I'll share these slides. that gives you more information about this project, or I could put it in the chat, I suppose. And the concern with frost action, of course, is that if you have access to water and if you have freezing conditions, then you can grow ice lenses. Here in the lower left is a dramatic example of a large ice lens. This can occur many meters. Here on the upper left is what happens if you have a road or other foundation system above that. You see this undulating variable surface. And this is what it looks like in a soil specimen where you grow these ice lenses. And the challenge is these ice lenses can grow very large if you have access to water, freezing conditions, and frost susceptible soils. So as an application for engineered water repellency, the concept is to avoid what you have here on the left, which is, let's say, for example, a road, and you have a water table, which in conjunction with a high capillary fringe can lead to a growing ice lens. So if we make the soil water repellent, we essentially prevent that from happening. And so we're funded to look at this in the lab with numerical modeling and in the field. So we collected soil from 4 different locations across the United States, in Alaska, in Iowa, in New Hampshire, and in North Carolina. And we've got, and so we have a robust testing program to test these soils. And of course, the broader objective is to look at all these kinds of applications. But for now, we're focused principally on road applications. And as I said before, one of the issues with freeze-thaw action, if you have a closed system, you're not going to have much heave, and frost action is not a problem. The problem is if you have access to water, you have an open system. That's the concern. Now, what's interesting about frost action in soils is, although this has been studied for over 100 years, it's actually, there remains a remarkable amount that is not understood in terms of the actual mechanism of water migration. There are different theories that people use to model this, some physical and some chemical, but a lot of the work that was done in the 1950s, 60s, and 70s, excellent theory. At that time, they didn't have as much analytical and microanalytical and testing resources. We are fortunately, all of us as a scientific community now have access to great resources. So when you look at what happens at the frozen zone and the unfrozen zone, you have this frozen fringe, and it's fascinating and what happens in the soil system when you freeze a soil sample and you form these ice lenses. And so if you look more carefully, what happens when you convert liquid water to solid ice, you exclude ions. And so this figure here on my right side of the figure is meant to convey what is happening. And so there's at least 2 mechanisms by which water is attracted to grow an ice lens. The first mechanism is the fact that as you convert liquid water to solid ice, it has the same effect as drying the soil. So as you dry a soil, you create suction, and you have a capillary gradient, a matrix gradient. So that's one mechanism. But the other mechanism is what we call this cryogenic term. And because you're excluding ions from water as you form ice, that increases our osmotic potential. So osmotic potential and matrix potential both serve to attract water. But what's interesting is there is, as of now, although I look for we have a number of colleagues on the line here, I would be interested if anyone wants to share information with me, but I have not seen literature which matrix potential from osmotic potential. And part of this research is intended to elucidate or to understand what is the gradient and what is the effect in terms of overall ice lens growth, decoupling the matrix from the osmotic. And so what that looks like, matrix potential, of course, is through the pore space, but you also have osmotic potential. This is meant to conceptually show from ions that are released from a growing ice lens above. You've got water that moves through the bulk fluid, but you also have water that moves through the diffuse double layer. And so we're looking at all of these things. So we have some laboratory testing that we're doing with columns of soil. So on the right here, you see a schematic of a column, and we give it a supply of water, and we put it in a chamber, and we freeze it. And so here you're looking on top of these specimens. These specimens are sitting in a freezer here in the left, and we conduct frost action testing with engineered water repellency.
You have about 5 minutes left.
Excellent. And so what you see here is when you make it water repellent, here is untreated, you have a higher, and then with treatment, you have a lower heave, which is what you expect. The next part is to model this, because if you want this, it is helpful if you can model the effect and get that modeling to agree in the lab so that you can predict how this will also work in the field. So here we have some physics modeling, and we're looking at temperature at the bottom, and then we have a cold surface temperature. How does that, depending on our boundary conditions, how quickly does that penetrate into the subsurface? So for example, we want to know if we're going to build something, where is that freezing front going to penetrate? So we can use modeling to predict where might frost, that frozen fringe occur, where might that ice land? And so what you're looking at here is a figure. Think of this as soil side. So the freezing front is coming from the right, unfrozen is to the left. We can model where that's going to occur, and that's helpful if we want to do this in the field. So here's a project in the state of Iowa. There's a lot of low volume roads that are critical to the agricultural industry. And so we went through a process of determining where we can treat this road. And so we went through and we tested about, these units, this overall section is about 400 meters or about 1,200 feet. And so we instrumented this road in Iowa. We had different instrumentation. We had 4 different cells, and these cells included a control cell as well as several cells types of treatment. And so I'll walk you through quickly how this was constructed, sort of in profile view and under construction and then instrumented. So this is what you're seeing. This is material, placing sensors, constructing this. So cell 1 and cell 2, this was sprayed at the surface. This was sprayed, and this was sprayed just at the surface for cell 4. And we continued with the instrumentation. And the whole purpose is to put instrumentation above and below where we made it. And so we will have data this winter season. It's rather cold in Iowa now, that will tell us, are we able to prevent frost action? And is the water repellent layer preventing water from moving through there? So here's a treatment. This is a section of the road. This blue line shows where it's treated, and we have instrument below that. This is cell 2. Cell 3 is our control with no treatment. And cell 4 is where we have 2 layers and instrumentation in between. We've used live, and we're going to scan it several times to look at the surface. We put in monitoring wells. This is how we treat it with, these are chemicals that we have. This is me dumping the chemical into the tank. Again, this is environmentally friendly, sustainable chemicals that we use to treat the road. And then you can either surface, you can mix it. This is a different method of mixing it with the road. And this will bring me to my closing thoughts. What's important with this kind of work is you want your laboratory testing to also match your, and if your laboratory testing matches your modeling, that gives you confidence to go in the field that you're able to construct this at a cost which is cost effective. And from here's us doing some instrumentation that we're putting that water repellent layer. So that's my closing thought, that having laboratory field and model, sure you have confidence that all agrees. Innovation is easier to demonstrate on the road, and you want to understand your objectives. This was the research team. This was this past summer. Team acknowledgement for all these people here at UNC Charlotte, one at Michigan State. And my final slide is a list of references. I realize 20 minutes is a very short amount of time to convey this, but I hope that pictures and the high-level summary, you can appreciate the broad of engineered water repellency. And if you have these papers, I would be happy to share them. Hopes that it is helpful to you, or maybe leads to some kind of collaboration. For your time, And I wish you success as part of the symposium. Thank you very much for your time.